In this mini clip, we will be looking at the applications of the logarithmic function. Our question reads, determine the pH of a solution that has a hydronium ion concentration of 7.45 times 10 to the exponent -3 molar. Since this question asks us to determine the pH, we're going to have to use our equation for pH, which is that the pH is equal to the negative logarithmic function of the concentration of the hydronium ion. This H with the plus sign is the hydronium ion, and these square brackets indicate that we're looking at the concentration of this ion. Our logarithmic function doesn't have a base written here. Whenever we write the logarithmic function without a base following, this assumes that we are dealing with a logarithmic function that has a base of 10. So now our question tells us that the hydronium ion concentration is 7.45 times 10 to the exponent -3. So we can substitute this number in for our concentration. Our second line will be that the pH is equal to the negative logarithm of 7.45 times 10 to the exponent -3. Because we're using a logarithmic function of a base 10, we can simply put this line into our calculator now, since the logarithmic function found on our calculator also has a base 10. So, putting the negative log of 7.45 times 10 to the exponent -3 into our calculator will give us a pH equal to 2.13. And with pH, we don't have any units, so this is our final answer. Now let's look at another question that is very similar. This question asks us to determine the hydronium ion concentration of a solution with a pH of 5.71. Once again, we're going to use our equation for pH. Now in this question, we're given our value of our pH, 5.71. So I'm going to substitute this number in for our pH found on the left-hand side of our equation. So our second line will be 5.71 is equal to, and I will leave the right-hand side of the equation as it is. Now we need to isolate for our concentration of our hydronium ion. So first off, let's get rid of this negative. The operation here is multiplication. A -1 times the logarithmic function of the concentration of the hydronium ion. In order to get rid of this -1, we need to apply the opposite operation, which is division. So I'm going to have to divide this side by -1. However, whatever we do to one side of the equation, we also need to do to the other side of the equation to ensure that our equality is true. 5.71 divided by -1 gives us -5.71, which is equal to, these two negatives divide out to be a positive, and we're left with the positive logarithmic function of the concentration of the hydronium ion. Now we've run into a little bit of a problem. We need to isolate for our concentration, but we have this log function out in front of the concentration. So in order to eliminate this problem, we're going to have to think back to our rules for the logarithmic function. What I'm going to have to do now is raise both sides of this equation to an exponent with a base of 10. So looking at my left-hand side, I'm going to have a power with a base 10, and this will now become my exponent. So 10 to the exponent negative 5.71. And I'm going to do the same thing on the other side. So we have a base of 10 to the exponent of the logarithmic function, the concentration of the hydronium ion. Now the reason why I did this is because if we think back to our rules for the logarithmic function, when I have the log of some number as an exponent with a base of 10, this is simply equal to the number following the logarithmic function. So our right-hand side of our equation is simply equal to the concentration of the hydronium ion. So raising both sides of the equation to an exponent with a base 10 allowed us to isolate for the concentration. Now looking at our left-hand side of the equation, we just need to put this into our calculator. 10 to the exponent negative 5.71. And writing our final answer in scientific notation, we should have our answer to be 1.95 times 10 to the exponent negative 6. And because we're dealing with the concentration of the hydronium ion, we need to include our units, which is molar. So here's our final answer. Now in chemistry or physics class, you may be expected to apply special rules for the logarithmic function to determine the correct number of significant figures. So I just ask that you check with your textbook.